Yeah, yeah.
Okay, I hope you all had a good long weekend. It was nice to have like kind of a little mid-semester break. Um, so I'm gonna start today by talking a little bit about the midterm. So the midterm, this is gonna be, I'm gonna release this tomorrow night. So I'll release sometime tomorrow. I can send an email or something when I do that. And it's due March 4th at 5 p.m. in Gradescope. And it covers chapters 1 and 2 in the book. And obviously it's a take-home midterm. So you have the entire time to work on it. So it's like 10 days. And my advice for this would be to probably sometime this weekend, read over it and think about the problems a little bit. If you don't have time to like actually work on it this weekend, like I think it's still good to just have the problems in your mind so you can kind of chew on it as time goes on, and definitely don't leave it for the last minute. So yeah, are there questions about it? About the midterm? Anything related to that? I just wanted to mention something so that it's like on your radar and you're not surprised when it just like pops up in Canvas. Okay, so we are currently studying the questions and moving into math. So we're looking at the question, how many spanning trees are there of a given graph? So just to kind of refresh, what is a spanning tree? It's going to be a tree, so connected and acyclic subgraph of G that touches all of the vertices. So it's a spanning graph. And last time we proved this proposition, which we'll need today, so I'll kind of remind you of it. So we gave kind of a recursive way to compute the number of trees of a graph. So if we let tau of G be the number of spanning trees of G, and we take E in the edges of G to be a non-loop edge, then we have that tau of G is equal to basically the number of trees that do not contain that edge plus the number of trees that do contain that edge, which we related to the following two graphs. So one is G minus E. So if we take out the edge E and compute the spanning trees of that graph, that's going to correspond to spanning trees of the original graph that just don't go through that edge. And then the other piece of this is tau of G contract E. So if we shrink that edge and merge the two vertices that are its endpoints, we get a graph which is G contract E, and computing the number of spanning trees of that thing will tell you how many spanning trees are there of G that do use that edge E. Okay, so this is just that's something that we proved last time. Are there questions? Okay, so we're going to use this today, but I'll remark that this gives us one way to compute the number of spanning trees of the graph G. So what might you do if you were handed some graph is you could just start deleting and contracting edges until you had all graphs that were simple enough to compute the number of spanning trees by hand. Okay, so that's like one algorithm that you could use to compute tau of G. It's just like begin deleting and contracting until you end up with really simple things. The problem with this is that it's going to be impractical just because the size of the computation grows very quickly. So this is typically not how people do this. And we will see a theorem today that gives you a very good way to compute the number of spanning trees of a graph G called the matrix tree theorem. So I'm going to set up like some notation for that. So let's so basically, how are we going to compute the number of spanning trees of this graph G? I'm going to write down a matrix, and then it's going to turn out that the determinant of that matrix computes the number of spanning trees. So let's write down that matrix. So I'm going to let G be a loopless graph with vertices V1 up to Vn. And I'm going to let A sub ij be the number of edges with endpoints I and j. Or sorry, I guess I called them V, so Vi and Vj. Okay, and then I'm gonna let Q sub G be the matrix with entry minus Aij when I is not equal to j. And then it's gonna have on the diagonal entries, so if when I is equal to j, we're gonna have the degree of the vertex V sub I. Okay, so this is what size of matrix is this? This is n by n, so number of vertices times number of vertices. So just to kind of like recap what this is doing, on the diagonal, we have the degree of each vertex, and on the off diagonals, we have minus the number of edges from vertex I to vertex j. Okay, so then I know this will be clear why we need to do this in a second. So I'm gonna let Q star G of I'm gonna use square brackets of V sub I. This is going to be the matrix obtained from QG by deleting the row and column corresponding to the vector, or sorry, to the vertex V. The matrix So we're going to delete the ith row and column. Okay, so just for sake of concreteness, let's do an example. So I'll do the kite from last lecture. So this was one where we had found all the spanning trees already. So it's this graph. And I'm going to call this V1, V2, V3, and V4. Okay, so I'm going to have you write down Q of G and Q star G of V3. So write down those two matrices and then also compute the determinant of Q G star V3. Okay, did you guys get the same matrices that I have written here? Did anyone compute the determinant?
Q star.
Uh,
Oh, yeah.
yeah, the determinant of the, yeah, Q star. Yeah, 8. Okay, good. And yeah, I know it's been a while, but we computed, like we found all the spanning trees of this graph last time, and we saw that there were 8 of them. So 4 that did not include this edge, just gotten by deleting one edge in this cycle. So there's 4 ways to do that. And then for the ones including this edge, we also had 4 because you can take either of the 2 edges on each side, and there's 2 times 2 ways to do that. Okay, so this is like hinting at what the theorem is, which is that the number of spanning trees is given by computing the determinant of this matrix, where you can just delete the row and column corresponding to any vertex. So maybe I'll just say why, like one thing about why we need to delete one row and one column. So if you look at this matrix, automatically this is going to have determinant 0 because, for example, if you sum across every row, you're going to get 0 because, like, what did we put here? We put the degree and then we put minus the number of edges going to each vertex. So this is always going to sum to 0. And that means that the columns of this matrix are linearly dependent. So the determinant will be 0. So if we're going to hope to compute anything at all, we need to have a matrix where the determinant is not 0. And so we'll prove why this is the one that does the right thing. Are there questions up to this point? Okay, then let's do matrix tree theorem. Okay, so this is called the matrix tree theorem. And all it says is that the number of spanning trees of the graph G is equal to the determinant of Q star G of V, where V is just any vertex of the graph. Okay, so that's the statement. And how we're going to prove this is by induction on the number of edges in the graph. So the proof will go by induction on the number of edges of G. So to start, let's do the base case. So this will be when the graph has 0 edges. So what happens when it has 0 edges? How many spanning trees are there? Yeah, there'll be 0 spanning trees. And what is the matrix Q star, or even just Q sub G? What does Q sub G look like?
0.
Yeah, so Q G is a 0 matrix. So that means that Q star G of V is also a 0 matrix. So that means that the determinant of Q star G of V is 0. Okay, so that verifies the base case because we got the determinant is 0 and the number of spanning trees is 0. Okay, are there questions about the base case? Okay, so now let's do the induction step. Okay, so we're gonna go ahead and assume that G has some number of edges, and for any graph with fewer edges, the statement is true. So we can assume that G has at least one edge. So let E be an edge of G. And we're just gonna say that the endpoints are U and V. So E is UV. Okay, so we had this proposition that said that the number of spanning trees of G is equal to the number of spanning trees of G minus E plus the number of spanning trees of G contract E. Okay, so the basic strategy is going to be to this is going to like be the statement that makes our induction go, because these two graphs have fewer edges than G. So we're assuming that the statement holds for these graphs. And so all we really need to do is relate the determinant of this matrix to the determinant of the matrices corresponding to these computations. So that's like the strategy. Okay. So I'm going to make a claim. Oops. And it's the following. So if I take Q sub G star of V, so I'm deleting the row and the column corresponding to one of these endpoints of E. I'm going to claim that this is equal to Q sub G minus E star of V plus E sub UU, where this is the matrix with a 1 in the UU entry and 0 everywhere else. So, oh, and I think that this should be, okay, let's think through this. So this is a 0 everywhere except in the UU entry. Okay, so let's see why this is. So if we're looking at the graph G minus E, so let's just quickly compare Q sub G to Q sub G minus E. Right, so what has changed between these two things? U and V have each lost a degree. So those diagonal entries will go down by 1. And in the UV entry and the VU entry, we've also lost something, right? But when we delete the row and the column corresponding to those two, we'll forget about that part of it. So all that we'll have is that in the UU entry, the degree has gone down by 1. Is this making sense? Would it be helpful to like do an example, or is this like, yeah, okay. So let's look at let's do like a really simple one. So let's just do like the triangle. And let's say this is U, this is V, and this is E. Okay, so what does this matrix look like? We have, and I'm going to put U and V first, because why not? So and then this will just be X. And they each have -1, -1. Okay, is that matrix looking right for Q sub G? Okay, and then what happens when we delete the edge E? Okay, so now U and V both only have degree 1. The stuff relating to, so the row and the column corresponding to X stay the same. But here now we have zeros. Okay. So then comparing, so yeah, so now what am I going to do to these two matrices? I'm going to delete the row and the column corresponding to V. So we've deleted that and we're deleting this. Okay, so all that's changed is that in that UU entry, we've gone down by 1. Because like what else changed between these two matrices? So the edges between U and V changed, right? But we deleted those rows and columns. So to obtain this matrix from this matrix, right, all I need to do is add 1 here, and that's given by this term. Does that make sense? So are we on board with the claim? Other questions? Okay, so then now we need to compute the determinant of this thing. Okay, so this was like an example. So now I'm going to look at the determinant of Q, G star V. Okay, so we said that this was equal to, we can rewrite this, so by the claim. So we have the determinant of Q, G minus E star of V plus E, U, U. Okay, so this is where it's going to get a little bit complicated. So I'm going to write out the like permutation definition of the determinant, and we'll kind of analyze to see what this is. So this is going to be the sum over permutations sigma in, so let's say, how many vertices do we have in here? Okay, well, these are, so if QG was originally an n by n matrix, then now we're looking at n minus 1 by n minus 1 matrices. So we have permutation. Okay, and then we need the sign of the permutation. And then we need the entry of this matrix corresponding to I comma sigma of I. And I'm just going to copy this. Didn't leave enough room. Okay, so I'm gonna tell you what this comes out to, so we can kind of argue our way towards that. So this is gonna come out to det of Q sub G minus E of V star. Okay, so we're preserving, it's like this part is somehow going to be preserved, and then the kind of extra bit that we get is gonna be the determinant of Q sub G minus E of V and deleting U. Okay, so let's argue why this is true. So, okay, so for one, we can split this into two parts, right? So we'll have one sum just consisting of these things. And then we're going to have another sum consisting of okay, so when right. Okay, so let's think about EUU. So this is 0 in most of the entries, except for the UU entry, right? So for the most part, this is gonna, for most permutations sigma, this is gonna be the same. So let's break this up into two sums based on whether or not the permutation sigma fixes U or not. Okay, so we'll have one sum over sigmas in Sn minus 1, where sigma of U is equal to U. Okay, so for all of those, when we take the, actually, let's do the not equal to U first. Okay, so for those sigmas, when U is not fixed, that means that the entry that we're taking, and maybe I'll rewrite this like this, sigma of I. The entry that we're taking here has not changed because we just added 0 to it. Okay, so we'll get here, we'll just have SGN sigma of Q sub G minus E star of V plus 0. Okay, and then we have some contribution from permutations that do fix U. Oh, not equals. So we need plus the sum over the permutations that we left out. And I'm missing, sorry, I'm missing a whole product here, right? We need just product over all the i's. Sorry about that. Okay. Okay, so then we're going to take the sign of sigma and the product as I goes from 1 to n minus 1. And what we're going to find so again, I'm gonna separate out the UU case. So we're gonna look at I not equal to U. And again, we'll have the same thing here. So QG minus E star V plus 0. And then we have this additional term corresponding to when I is equal to U. And there we will have, and this should be, oops. We need the indices here. So then in the UU entry, we're gonna get a 1. So we'll have Q G minus E star of V. And we're looking at the UU entry of this plus 1. Okay. is it making sense up to this point? I know this is like really calculation heavy. Does anyone have any questions? Or are we good up to this point? Okay, so now we need to add, we're gonna have another step here. Okay, do we see the determinant of Q star G minus E in this? Do we see where that is? Yeah. So almost we're missing some of the permutations. We're missing the ones that fix U. But we get those again from this term, right? So like if we, so imagine breaking up this part into two things, one where we've multiplied by this and the other one where we've multiplied by 1. Then for this part, we've recovered all the terms that we're missing from here. Does that make sense, or should I write it out? Okay, so one part that we get is, and maybe I'll color code this. So we get the determinant of Q star G minus E of V. Okay, and that comes from this and like multiplying out and looking at like the parts coming from this factor. Okay, so then what is left for the parts corresponding to the +1? So that's plus the sum over permutations that fix U. So we could just think of that as permutations from Sn minus 2, because we're just ignoring the U. SGN sigma, and then we get the product as I goes from, I'm gonna just write this out the way that it is. So sigma of U. So that fixes U. We're going product I not equal to U up to n minus 1. And then we just get the this part. So we have Q G minus E star of V. And we're taking the I sigma I entry of that. Okay, are we good from how we got from here to here? Okay, so now all that's left to do, so this part, oh, I forgot a parenthesis. Okay, so this part equals this part. So now all that's left to do is convince ourselves that what is written here is equal to this. Right, so do we see why that's true? Oops, and this should have a star as well. Yeah, so like what's written here, this is the determinant of a matrix where we're just ignoring the youth I and column. Right, so this is determinant, this is the determinant of this matrix where its youth I and column, I row and column has been deleted, which is this. Is that good? So that gives this term. Okay, so let's recap what we did. So we took the determinant of the matrix that we wanted to, and we found that it broke up into these two terms. Okay, so that's where we're at. Now what we want to do is use the induction hypothesis via this result to somehow relate these two determinants to a computation of like how many spanning trees does some graph have. Okay. So what do we have here? So by the induction hypothesis, what is this computing?
Trees of G minus E.
Yeah, so this left-hand part is tau. Let's do this. So this is tau of G minus E by the induction hypothesis. So then what we want is for this to be equal to tau G contract E, and then we're done. So what we want is that this is tau G contract E. Okay, so let's argue why that will be true. So the first thing that I want to claim is that Q G minus E star V U, so this matrix that we have, that this is equal to the determinant, or sorry, not the determinant, just the matrix Q G V U. Okay, so why is that equation true? Why are those two matrices the same? So these two. Yeah. Yeah. So like, yeah, so if we wrote down this matrix and compared it to this matrix, QGE, sorry, QG minus E, this one is only different in the rows and the columns corresponding to V and U. So if we delete V and U, it's like this never happened. So yeah, so these two matrices will be the same. Does that make sense? Yeah. Thanks. Other questions? Does that make sense? Okay, and then I want to further claim that this is also equal to QG contract E star of V. So why is that true? Or rather, okay, wait, let me take this back because these matrices don't even have the same size. So now I'm just going to compare the determinants. So now, so we verified this claim. Second claim, the determinant of QG star U, or sorry, VU is equal to the determinant of QG contract E star of V. Okay, so why does that equation hold? Maybe for this one, it'd be helpful to do an example. Okay, so let's do the kite. Where this is VU. And this is E. And then, oh, and we're contracting it over here. Okay, and then I'll call these X and Y. Okay, so this matrix is 3, 3, 2, 2. Okay, so then we're going to delete the row and the column corresponding to U and V. You know what? Maybe we are just going to get the same matrix. Okay, so I was confused for a second. I thought that these two matrices were going to have different sizes because over here we deleted 2 vertices and over here we only deleted 1. But what else happened? We contracted an edge, so that also lost a vertex. So these two matrices are going to have the same size. So let's just finish the example. So V has degree 4, has 2 edges to each of these guys. And then X and Y each have degree 2, and they have no vertices to each other. Okay. Okay, so we did end up with the same matrix. So what happened? So when we went from here to here, we contracted the edge. So that means that the vertex V, this new vertex, like the merged vertex, has all of the same edges coming out that the old graph had, right? So it has the same number of edges to X and Y as V and U did total in the old graph. So, and then what else? It's I'm not seeing like a quick explanation as to why these two matrices are the same. So I guess like what stayed the same? Like we didn't change the degree of X or Y, like we left those vertices alone. They have the same degree and they have the same number of edges to the vertices that are not U and V, which are the relevant ones to the matrix that we're looking at, right? So these entries will stay the same because they maintain the same degrees, and the number of edges to vertices other than V and U will stay the same. Okay, are we good? Does this make sense? So we verified both of these claims. Okay, so that means that what happens here? The determinant of this matrix, so via these two claims, is now the determinant of this matrix, which is, so like, let's go back to our equalities, our chain of equalities. So we have tau G minus E here, and now we're replacing this determinant with the determinant of Q G dot E star of V, which then again, by the induction hypothesis, is gonna just be the number of spanning trees of G contract E, which by our proposition is equal to tau of G. And that finishes the proof. Because like, where do we start with this? We started with the determinant of this matrix. Okay, that was a very involved calculation. So I think it'd be completely reasonable if you all had questions, or if it just takes time to absorb it and you have questions later. The book has a different proof. So if you didn't like this one, then you can look up another one. I actually didn't like the proof in the book, so I went looking for a different proof, and I found this one, which like, I don't know, it speaks to me more. I like this like inductive way of like deleting edges and then arguing about like why the matrices are what they are. But okay, are there questions now? Yeah.
I think it's sort of a question, like, why did you go a little bit?
Yeah.
Back when we have like the permanent calculation.
Mm-hmm.
I don't really understand like well, actually like the one below that. Maybe go like to the next, well, the next line like going down.
Oh, here. Wait,
Yeah.
this line?
Or well, the one below that. Like, how can you go from? Like, I know you
Like-
said that it's equal to the determinant of like 2 star E, like, minus E, removing E and U, but like, I don't understand how you can say that if you're only including the permutations of U that are equal to U. If the sigma U is equal to U, because isn't that not all of the possible permutations? Or all the rest of zeros you cannot include?
Yeah, so like, okay, so let's think about like, I'm gonna draw a picture of a matrix. So let's say we have like some entries. And let's say this is the UU column and row. So what the determinant wants to do is like pick like non-attacking rooks inside of this, right? So if we pick a permutation that fixes U, then our options are to do this, or like that. So what that is actually looking at is just the determinant of that submatrix. Yeah. Does that make sense? Yeah. Are there other questions? Okay, so I'm gonna talk about so this was the matrix tree theorem. So like one thing that you can do with this, for example, we like going back several lectures, we talked about Cayley's formula for like the number of trees on n vertices. So like one thing that we could now do is reprove Cayley's formula using the matrix tree theorem by just looking at like how many spanning trees are there of the complete graph. And that's like a really good thing to work out. So like this is like an exercise. Verify Cayley's formula by computing the determinant of the matrix corresponding to the complete graph minus a vertex. So this is like, I would have included this on the problem set, but it's due tomorrow. So you just wouldn't have had enough time since we learned the matrix tree theorem. Then the next thing is the midterm, so we won't have a problem set covering the matrix tree theorem. But like this is like a really good exercise to work out if you want something to try. So then the next topic is about optimization and trees. So one concept that we haven't touched on yet, but that comes up a lot is of a weighted graph. So a weighted graph is a graph where we're gonna give each edge a non-negative number. So this is a graph G with non-negative numbers labeling the edges. So for example, you might have a graph like this, and then all that we're doing is assigning numbers to the edges. And the reason for this is that this comes up a lot in applications. So for example, these might be cities, and the edges denote distances between them. I guess, and this is not a realistic example because it fails the triangle inequality, but you know, maybe this is like the toll cost for driving across this road or something. So if you want to go from this vertex to this vertex, like, oh, it's actually cheaper to go this way than this way or something like that. So this comes up a lot in applications, and because of that, there's a lot of like algorithms for determining things such as like the shortest or cheapest path between two vertices, or like the spanning tree with least total weight. So like, what might that be? Or like correspond to? Maybe you want to build a subway system that like hits all these different locations, and so you need like a spanning tree, and you want that spanning tree to have like least total distance or something like that. So anyways, I'm gonna talk about two, well, I don't know how much we'll get through because we don't, maybe one algorithm relating to spanning trees. So the first one, and if we don't do the second one today, then we'll do it next time. This is called Kruskal's algorithm. So what this does is this finds the spanning tree with minimum weight in a weighted graph. So like, what is the weight of a spanning tree? Just add up the weights on all the edges. So this finds the spanning tree with minimum weight. And one thing that's kind of funny in this case is that it turns out that the most obvious solution works. And this is like an example of what's called a greedy algorithm. So I'll explain how the algorithm works, and then I'll come back to that comment about why this is like the easiest possible thing that you might imagine doing. So our input is going to be a weighted connected graph G. And the output is going to be the spanning tree with minimum possible total weight in G. Okay, so here's what you do at each step. So the iteration is of whatever edges of G are left, you'll consider the one with lowest weight. Okay, wait, let me start over. So let's start with H having no edges in it. So we'll start with E of H equal the empty set. And then what we're going to do is like successively add edges to H. So at each step, we're going to consider the edge of lowest weight that's remaining. If it joins two components of H, then add it to H. So AKA adding this edge does not create a cycle in H. Then we're going to add it, and otherwise I'm going to discard it. And then we'll just stop doing this whenever H is connected. So I'll write something down. So of the remaining edges of G, we'll consider the one of lowest weight. If it joins two components of H, then we'll add it to E of H. Otherwise, we'll discard it. Yeah. Yeah, H is going to be the output tree. So for our output, yeah, we'll have a spanning tree called H. So we'll end this when H is connected. And then that's going to be the spanning tree of minimal weight. So basically, like, why is this like a greedy algorithm, or why is this like kind of the simplest possible thing you could imagine? It's because, like, what are you doing at every stage? You're just doing whatever seems optimal at that moment. So it turns out that, like, for some algorithms, like doing the locally most optimal thing will not get you to a globally optimal solution, but in this case, it does work. So I guess that's like a theorem that I'm not going to prove, but that this algorithm does yield the optimal solution. So I'll have you all work out an example. Oops. See, I'll just make up. Okay, let's do this. I'll put some numbers on here. Okay, so go ahead and look at this and find the optimal spanning tree. Yeah.
Using that,
Oh, no. So one thing that the book completely glosses over is what to do if there's two edges with the same weight. So I looked this up just now, and you can just pick either one. Yeah. So if your minimum edge has, like, if there's two, say two of these edges had weight 1, it's like this one was, we could arbitrarily pick this one over this one, or vice versa. And you'd get a spanning tree of minimum weight. I don't know if it's possible to get different spanning trees, but I guess like the theorem would say that they both have the same weight. It's kind of interesting. Okay, let's run through this really quick. So so the first one that we would add would be this one, and then the next one of lowest weight is this one, and the next one is this one, and then here we're gonna have to add a lot of edges before we encounter any problems. Okay, so the edge labeled 7, if I added this to my spanning tree, well, it wouldn't be a tree any longer. So I'm not going to add this one. So we'll cross that out. And then 8 is the next one. And then there wasn't a 9, and here's 10. And it looks like now we have a spanning tree. So we're done. Okay, so that was Kruskall's algorithm. And then the next one that I wanted to show you all was Dijkstra's algorithm. So what this does is it's going to find a path of least weight from one vertex to another. So in a weighted graph, we're going to redefine what distance is. So in a weighted graph, we'll say that the distance between two vertices is the minimum sum of weights of edges in a UZ, in a path between, so here, I'll write this out. So the distance between vertices U and Z. So this used to be the length of a shortest path between them, but now I'm going to say that this is the minimum over UZ paths of the sum of the edge weights in that path. So to look at an example, say I wanted to know the distance between these two vertices. There's a couple of different paths between them. One goes this way, one goes this way. And then there's also like, you could go like that, but the one of minimum weight is this. And so I'd say that the distance between them is 12. Does that make sense? Okay, so that's how we're gonna define distance for weighted graphs. And I'll denote the weight of an edge by W. Denote the weight of an edge by W of UZ, if UZ is an edge. And additionally, if UZ is not an edge in the graph, then we'll just take the convention that W of UZ is infinity. So if UZ is not in the edges of your graph, then we'll just say that the weight of that is infinity. Okay, so for the algorithm, our input is going to be a weighted graph G together with a vertex in that graph. And then the output is going to be the distances from U to Z for all Z in the graph. And furthermore, it finds those distances in increasing order. So the first distance that we'll find is like the closest one, and then we'll just go up from there. So to start this, so our initialization, we're going to set S equal to U. Oops. And I'm going to think of S as being the set of vertices where we already know the shortest path. So this is, think of as the set So as we go along, we'll be adding more and more vertices to S as we learn the shortest path from U to that vertex. And then I'm going to set T of U equal to 0 and T of Z equal to W of UZ. So what are we thinking of this as? This is going to be recording the length of the best path that we know at this moment. So records the length of the best path.
What is T here?
What is T?
Yeah.
Okay, so this is like some function that we're going to update as we go along. And at each step, it's just going to record the length of the best known path. So like to start off, we know that the distance to U is 0. And we know that the worst case scenario, the distance to Z is given by the weight of the edge from U to Z. So as we go along in this algorithm, we're going to update S and T. And so here's how that will work. So for our iteration, I'm going to select a vertex V outside of S. such that T of V is minimal among such vertices. And then what I'm going to do from there is I'm going to add V to S. And then I'm also going to update this number T of Z. So for each edge, VZ for Z not an element of S, I'm going to update T of Z to the minimum of the former known best value and T of V plus the weight of V to Z. Okay, so maybe I should try and draw a picture of this. So let's say these are our vertices in S, and then this is some vertex Z outside of there. And maybe the best path known to us so far went like this, but now we've added an additional vertex to S, which is V. And potentially, and we also know, right, we know how to get the shortest way to get to V. So potentially there's a faster way to get to this vertex Z by first going to V and then going to Z. And so that's what this minimum is going to record. Like we'll look at, we'll compare the old known best path to the one that goes to V and then from V to Z. Okay, so then we're going to continue this until S is equal to V of G, or T of Z is equal to infinity for all Z not in S. So if the graph is disconnected, this can happen. And then at the end, we know that the distance, so at the end, the distance from U to V is going to be this number TV for all V. Okay, so we have like 1 minute. So I'll give you an example that you can work on if you want to. And this example is worked out in the book as well, so you can compare what you get. And we'll stop there. So if you want to hang back and work out this example, you can. And other than that, I hope you all have a good weekend, and I'll send out a message when I release midterm.